Okay. Good morning. Well, welcome everybody. Thank you. I'm Michael Coden. I'll do the first part of the presentation, and then Mike Stormbreaker will come up here and explain what I said. The conference guidelines said we should tell you what kind of questions we're going to ask, and I'm going to ask you all in a short time how many state variables. So think about this. You think a modern operating system needs to manage. How many, could an operating system be designed to self-attack cyber attacks? And we're going to answer that question in the affirmative. And can an operating system also self-restore itself to the pre-attack state? Again, we're going to give you an affirmative answer to that. And we're also going to tell you where you can find open source code to try this new operating system approach. So I just wanted to start off with, Unix was invented about 50 years ago by Ken Thompson and Dennis Ritchie. And I love this picture, which comes from Wikipedia. I could have taken it myself because I was there when I was a recent MIT graduate. I worked for a company called Digital Equipment Corporation, which made that big wall of equipment, which was a PDP-1145, had a single CPU and 128 kilobytes of memory. And it took that much space. And that was the computer on which Ken and Dennis developed Unix. It's the same computer that Linus Torvald used to develop Linux. And that's what the operating system was developed on and for. And now what we've done is we've added lots more CPUs, lots more memory, lots more applications and processes that we want to run. And so I want to get a few guesses from the group here, the audience, as to how many times more state variables you think a modern system with Linux, Kubernetes, running a modern application is actually running. How many more state variables does it need than the original Linux, Unix of 40 years ago? Pardon? 1,000 more times? Okay. Now remember, back in those days, you probably had a few dozen state variables. So you think more like 12,000 or 20,000? Yeah. Anybody else? Sorry? Tens of thousands, okay. Any higher bidders? It's millions. It's millions times more state variables. And by trying to manage all these state variables, we've taken an operating system which was providing some basic services, file structure, inter-process communications, scheduling, and turned it into this inefficient database management system where it's managing millions, dozens of millions of state variables. And so what Mike Stormbreaker and the team of MIT and Stanford faculty and students determined was that this is just a database problem. And in fact, moving all those state variables into a database would make the operating system much more efficient. So what was proposed about 3 years ago by Mike and the team is that you start with a minimal kernel at the bottom, which is like the lowest level drivers that you would have in a Unix system, drivers in memory management, byte movement. And then on top of that, instead of putting an operating system like Linux and a container management system like Kubernetes, you put a distributed database management system directly on the bare metal, on the microkernel. And now the operating system services that you would expect an operating system to have, such as file structure and inter-process messaging and scheduling, are all done in tables in the database management system using SQL as the operating system language. And then on top of that are your user applications, which primarily run as stored procedures. So all the functions that you're used to seeing are here, but it's kind of upside down, where the operating system is a database and the operating system functions are performed by SQL, and the applications actually run in the database, and all the state variables are stored in the database. So the old mantra was that everything was a file, and that's how you sent information between different parts of Linux. That's how you did scheduling. That's how you did all your messaging. And now what we believe is that everything is just a table. And the table is much more efficient and much more secure. So if I want to send a message from one process to another process, the first process puts an entry in the table next to the name of the other process, and the message is sent to the other process. If I want to schedule a resource, I go into the table. If the resource is available, I put my initials next to it, and the resource belongs to me. When I'm done with the resource, I take my initials away, and it's available for everybody else. No files are needed to send, just a SQL query to take the resource, a SQL query to give it back, okay? So we put all the OS in these database management system tables, and guess what? All the OS state, all the app state, all the database management state, and now all our log files are in a single table, and by using SQL queries, we can detect any anomalies in those log files instantly, almost instantly, a few hundred milliseconds, and that's how we can detect cyber attacks. And you'll see after Mike, who should come up now because he's supposed to do the next slide, and you'll see that it will also allow us to roll back the operating system after we block the cyber attack, which we're going to demonstrate to you, and actually be at the pre-attack state within seconds of the actual attack. So,
okay.
Mike.
Thank you, Michael. Michael, as you can imagine, used to be the cybersecurity director for the Boston Consulting Group. So any talks he presents are lots of pictures. Unlike Michael, I'm on the faculty at MIT, so I'm an academic. My main claim to fame is that I won the Turing Award in 2014, mostly for my contribution to Postgres. So academics use small numbers of words and very few pictures. Here we're seeing lots of pictures. So anyway, I just want to stress very clearly two things that Michael said. So the picture of Ken Thompson and Dennis Ritchie was very reminiscent because I knew Ken Thompson pretty well. He, in fact, visited Berkeley for a year in 1975, I believe. And Berkeley was one of the earliest Unix users in 1974. And what you saw was Ken Thompson and Dennis Ritchie worked for Bell Labs, so they had a lot of money. They had a big PDP-11. We had scraped our pennies together and got a PDP-1140 with 48K of memory and 20 megabytes of disk. One of the environments that our system runs on is the MIT SuperCloud, which is in Holyoke, Massachusetts. It has 9,000 cores, several terabytes of main memory, and many terabytes of secondary storage. So the scale has gone up by 5 or 6 orders of magnitude, and the amount of tasks, messages, resources that you have to manage has gone up by the same amount. So without us saying another word, managing operating system state is a database problem. And that's how we view it, and of course, we're the database guys, so that shouldn't surprise you. The other thing I want to stress is that you're all used to running the database system as an application to the operating system. That's the way all database systems run. We don't do it that way. Since operating system state is a database problem, we run the database under the operating system. So all operating system services, send a message, open a file, schedule a task to run, Those are all SQL applications to a database system. And of course, we run if you want to go fast, we run a very high performance main memory, multi-core, multi-node, serializable, partitioned, highly available DBMS. So the performance numbers you'll see are on a current commercial DBMS running at the bottom of our system. We're using VoltDB. There are a few other options that are pretty fast. Okay, so if you do things this way, it has an enormous number of benefits. Benefit number one is, suppose you want to find out which of your users is chewing up the most space, counting only those files bigger than 50 gigabytes. Well, if that's what you want to know, and you're running Linux and or Kubernetes and or whatever, you have to start doing kernel programming in C or C++, and in a month or two, you might generate the answer. In our system, that's all in the database system. You just run SQL, you get your answer in seconds. So basically, analytics are much easier to write. Monitoring, as you'll see in a minute, is wildly easier because everything's in one place. And that gives you some really interesting security features that we'll talk about at some length. So anyway, just think security. The other thing is think simplicity. So you're probably used to running Linux plus Kubernetes plus some security stuff. Linux doesn't have a transactional file system, so you may be running one of them. And then if you want high availability, you're running something else to do that. So all that stuff goes away, every single bit of it. So all you need, if the operating system is in tables, well, VoltDB is multi-node. Run it over however many nodes you want. And it's highly available. So if there's a failure, the underlying database system fails over and keeps going. And everything is a transaction to a database, because that's what databases are very good at. So your world is much, much simpler. And when I sort of explain all this to operating aficionados, people like John Oosterhout at Stanford, they rightfully so feel very threatened. Because what is this? This is the database taking over their turf. And so they can't object to life is simpler and has a lot more interesting features. So the only thing they can object to is you can't possibly make this fast enough. So it's going to be too slow. I've heard that refrain before. In the early days of relational databases, that was what the naysayers all said, and look at where that got them. So we started this project almost 3 years ago. As Michael already said, the actual genesis, the spark that started this, was I listened to a talk from Matei Zaharia, who is Mr. Spark and one of the founders of Databricks. And he explained that Databricks was routinely managing 1 million parallel subtasks on a big cloud. And he said, we have to schedule 1 million things. And he said, the only way we figured we could do that was to use a database system. So at the time, I don't know what they're doing now, but at the time, they were putting all of these million scheduling events into a Postgres database and using that to do scheduling. So, and he was, of course, complaining about performance. So I said, boy, we can do a lot better than that. So that was the seed, which is big, what you would think of as application systems, do scheduling of lots and lots of things. And anybody who's got to schedule a lot of things figures out that they need a database. And that's what Databricks did. So, can we make this fast enough? A simple answer is yes, we did. So this is blindingly fast, mostly because the DBMS we're using is blindingly fast. So what did we do in the first year of the project? We had to prove that the answer to that question was yes. So we implemented a file system, and we implemented a messaging system. We implemented a bunch of schedulers, all in SQL, all on top of VoltDB, and an open source version on top of Postgres. And we had this running on the MIT SuperCloud that I already talked about, also on GCP. And unless you squint, performance is about the same as current systems. So just for example, what does our messaging system look like? As Michael explained, it's a single table. There's a sender, a receiver, and a payload. That's a single VoltDB table. It is partitioned. So it's partitioned on the receiver ID. So if you want to send a message, you do a SQL insert, and that's all. That tuple goes into VoltDB, and since VoltDB is partitioned, it ends up in the partition that is on the receiver's home node. So what does the receiver do? He runs a SQL query to get the payload. So he does a SQL query followed by a delete if he doesn't want to keep the message. So the messaging system is all in SQL. Now, before you get too scared, if you put it in the database system, then if you want to change the messaging system to do multicast, all you have to do is insert multiple tuples into this message table, and you automatically get multicast. So doing things in SQL means that if you don't like the specific features that we happen to implement, feel free to go ahead and change them. Okay, so what's the performance of our system versus gRPC, which is probably what most of you are using? It's about the same. Some things are a little faster, some things are a little slower. It's, to a first approximation, the same performance. We compared our file system, which, to no one's surprise, is a blocks table, a file table, and a hierarchy table. And we compared that to both the Linux file system and also to a file system called Lustre, which is what the folks on the SuperCloud seem to like, because it does parallel read of big things by partitioning the data. So we're the same performance as both of them. What's more, if you want to move from the Linux file system-like thing to a Lustre-like thing, you just repartition the data and you've changed the behavior, because instead of partitioning on user ID, you partition on block ID, and that changes the behavior completely. So very flexible, and if you don't like it, it's easy to change. So basically, what we've done is prove that it's competitive with current technology. So you don't give up anything to run this. It runs at the same speed as whatever you're doing now. Okay, so far, life is good. So that gave us the courage to keep going. And the next thing we did was added provenance to what I've already talked about. And also we built a programming environment so you can run applications in our world. Okay, so how does provenance work? Well, remember that all file data is in the operating system in tables. All scheduling events are in tables. All messages are in tables. So we can capture any change to the operating system state. That's just standard database system log processing, something we understand, well, something database folks understand very well. So you basically keep a record of everything, and I mean absolutely everything, because all operating system state is in the database. There's no state anywhere else. And you just ruthlessly enforce that, and it's just as fast as whatever you're currently doing. And so all we do is change capture in VoltDB, and we're capturing all events. You can optionally capture all reads as well as all writes. And so the question is, how much does this cost you? The answer is about 5%. So you can keep a complete history of everything with 5% overhead. So you're about to tell me, yeah, but I've got a state in my current programming world, which I've stored in non-persistent application variables. So what do we do about that stuff? The answer is do what the operating system does. There's no reason why you should do anything else. We're fast enough. Store your application state in the database system in tables. That's in the same database that's storing all this other stuff. So everything is in one place in tables. That has some very nice features, because instead of you having to find 100 application logs, capture them all somehow, merge them together so that they're in time order, and then store them someplace, that's all happening automatically without you doing anything. So a unified event history of everything, your application state, all the operating system state, is in one place, in us. So the next thing you're about to say is, yeah, but this provenance is going to be very big. And you're running on a main memory DBMS, VoltDB. What do you do? Well, of course, we don't store provenance in VoltDB. We spool it transactionally into a data warehouse. So this is a big historical database. Data warehouses are very good at this kind of stuff. So we're using Vertica for now, which is another company I started 1 million years ago. If you'd rather do it in Redshift, that's fine. If you'd rather do it in Presto, that's fine. Use your favorite data warehouse, and we simply spool everything into a data warehouse. And they're very good at storing petabytes. So if you want to keep the log for a few days, fine. Keep it as long as you want, as long as you're willing to pay for the storage, keep it for however long you want. So basically, the log, history of all events of everything, goes into a data warehouse. And then, to no one's surprise, you want to know anything about what's happened to your world, just code whatever you're interested in SQL, because everything is SQL. So then the question is, well, how did this work out? Well, we compared this against one of the very popular monitoring systems, which, and I shouldn't say which one we used, but one of the very popular ones. So this system, what we do is everything goes into VoltDB in SQL, and then we capture all changes in binary transactionally over to a data warehouse. And then if you want to look for outliers, you just code them in SQL to your data warehouse. So that's what we do. What do you do if you want to run a conventional tool? Well, you have to write an adapter that captures data into their system. So it turns out we did that. We captured any changes to VoltDB tables into this other system. Along the way, it converted binary to CSV. Then they turned it back into binary, stored it in their storage system, and then they wrote monitoring queries in their proprietary language. So how did that work out? Well, we were faster. And the simple reason, there are two simple reasons. The first one is we don't have to convert everything to CSV and then back, so it just lower overhead. And then SQL data warehouses are awfully good at historical queries, and they're just better at historical queries than the security guys. So ingest is faster, and it's easier because all you'd have to do is write application state into a SQL database. You don't have to do a custom adapter to some other world. So ingest is faster and easier. And queries are easier to write since SQL, everybody knows SQL, and proprietary security talk is just not as easy. And it's faster. So it's all goodness. Nothing is bad here. You get the same performance as now, and you get a world which is faster and easier. So you say, well, suppose I want to write some more monitoring queries. Well, that's fine. Go ahead and do it in SQL. We actually wrote a machine learning system that takes a history of events that your guys notice are bad, and we trained an ML system to paw over the vertical log and detect outlier events. Runs great, blindingly fast, because everything in this system is blindingly fast. Okay, so provenance worked out great. So then what did we do? Well, if you are paying any attention to the world around you, your company is trying to move everything they have to the cloud as quickly as they can. So the cloud is the answer. Why is the cloud the answer? Well, let me just give you a quick vignette, which is Dave DeWitt, my colleague now, used to be work for the Jim Gray, well, he was the director of the Jim Gray Microsoft Systems Lab. And he said, here's, this was three or 4 years ago, here's the technology they use for data centers. They're shipping containers in parking lots, stuffed with boards, sealed, power in, internet in, chilled water in, otherwise sealed. And there's a bunch of shipping containers. Roof and walls optional, only there if you need it for security. They put them in places where power is cheap. And then they're sealed. And so if a board goes bad in the shipping container, they simply swap it out. They simply logically swap it out for a different board. If enough boards go bad, they bring in a forklift and swap out the shipping container. Now compare that with whatever you're doing for a data center. It's probably on raised flooring down the street in high expense, no longer high expense San Francisco. But anyway, I guarantee you that they can do it cheaper than you, much cheaper. So over time, regardless of what their pricing is now, there will be a race to the bottom, and they will be doing it cheaper than you can do it. And they are managing everything, and you don't have to. So we're all going to move to the cloud with everything that we're legally or software possibly, everything you can. So the other thing is that if you put stuff up on the cloud, all the cloud vendors make it highly financially attractive to run software as a service. Think AWS Lambda, think OpenWhisk. So if you structure your applications so that they're a collection of operations in a workflow, and every operation is stateless, meaning it passes its results either as an argument to the next guy down the line or through storage, i.e. through S3. So if you do that, it's just plain cheaper. So you move to the cloud, the obvious thing to do is to restructure your apps to use function as a service, software as a service, serverless environment, however you want to think of this. Okay, so what we did was we said, yeah, that's the world that's coming, so we'll build to that. So we encourage you, what we offer is write a collection of Java, write a Java workflow using Spring or whatever your favorite Java development environment is. Hand it to us. We take every operation and make it a stored procedure in the database. And we have a little bitty orchestrator that basically wakes up a downstream neighbor whenever its inputs are available. And all state goes through the database, just like by now you should realize that that is the universal answer to where is your data. So we built this, or I didn't build it. Ken and Peter, stand up, who are in the third row, they built it. And so what happens is that stored procedures are just plain fast. They're faster, There's a universal adage that you should all tattoo on your brain, which is you want to move the program to the data, not move the data to the program. It's just plain faster for data-intensive applications. And if you're not running a data-intensive application, we still work pretty well, but we work really well on data-intensive ones, which should surprise no one. Okay, so we compile into a collection of stored procedures that we orchestrate, and they are run inside VoltDB, and they are blindingly fast. So this environment is about an order of magnitude faster than AWS Lambda. So you just run a lot faster because you want to move the program to the data, not vice versa, and that's what AWS Lambda does. So this is blindingly fast, plus it has some other really nifty features. If there's a crash, we automatically fail over because VoltDB fails over. So you get HA without you doing anything, and all of your operations are transactional, because they just are, because that's what's provided by the database system. So let me just tell you one single bit about debugging. So any of you who are writing distributed applications, you have a problem debugging them, I almost guarantee. Why do you have such a problem? Because you have parallel threads or tasks or processes in your application that are doing stuff in parallel. And so the biggest fear of any system vendor is a customer says, I have a bug, here's a script that explains the bug. So you put up the script on your world, and if it can be reproduced in your world, you stomp the bug almost immediately. But if it can't, unreproducible bugs cause, if the customer is important enough, you put engineers on airplanes to try and figure out what's happening. What's going on, chances are it's a race condition between parallel stuff that's going on in parallel that somehow interacts. Well, in our world, you're welcome to have parallel Java operations going on, but they're synchronized transactionally through the database, so unreproducible bugs don't happen. And so this is a more reliable and easier to debug world. So again, nothing but goodness. Faster performance, better features. Okie dokie. So we said, I wonder if anybody is interested in a system with these kind of features. So I say Michael Coden, in his role through the Boston Consulting Group, put us in touch with a whole bunch of real-world enterprises, people just like you guys. And so we asked people, here's what we have, what do you think? So we got two kinds of very positive reactions. The first one was from two different Fortune 50 companies who basically make stuff. I call them scuff shoe enterprises because they're full of engineers who know about bending metal and doing all that kind of stuff. Okay, and they were both highly interested in the security benefits we had. So one of them uses one of the vendors at the show to capture events off of 100,000 endpoints. Big company. Endpoints are your computer, all the servers, all the factory floor gizmos, everything. They feed that event log into their proprietary workflow system, which enriches it with company-specific data. They then feed that to another vendor who is present at this conference, and that vendor stores it, and you write outlier detection queries in their system. And if an outlier is detected, they pass it to a human who verifies that it's really an attack rather than some benign thing. And from the start of an attack until they take action is an hour. And they are terrified, especially of ransomware, because they know a bunch of their buddies who have had totally unpublicized successful ransomware attacks that have cost $1 billion. So production is down for days to weeks, and that terrifies them. So in our world, we can detect all this stuff faster without going through multiple systems and all kinds of glue. And what's more, at the end of all this, if you decide something's an attack, it's up to you to figure out how to recover. Vendors typically don't have get back up code. And so if you want to get back up in our system, well, we have a complete event log of everything. So just back up the operating system 18 minutes. That backs up all your stuff. You let it go again. You're now in the pre-attack state. And you just roll forward, deleting the bad guys' stuff. So we provide resilience. And the general theme that all of you should really internalize is that successful attacks are inevitable. They will happen. And resilience is an absolutely essential feature. Lowering the amount of successful attacks is, of course, great, but there will be some that get through inevitably, and you need to get back up. So we detect attacks quickly, and we provide automatic get back up. Okay, so security is really great. We also have been talking to some fin services companies. My favorite example is what's called once and only once, which is, suppose you want to move money from an account over here to an account over there. So you debit this guy, you send a message to that guy saying increment him. He sends a message back saying, yep, I did it, and then you commit the transaction. That's what you'd like to do. Since we run the messaging system and the data, that's simply a single transaction in our world, and you commit or abort that transaction, and it works like a charm. In the current world, in FinService's current world, you need to have a distributed transaction between the message system and the database system, and nobody supports XA, which is a distributed commit protocol, so you have to write your own in application code, and it's tricky and a real pain in the butt. So lots of people have found this intriguing. So our point of view is this is nothing but goodness. You get way better security, unified logging, way simpler. You can get rid of your Kubernetes system administrator. Life is just goodness. So you say, well, can you really give us a demo? The answer is sure. We have a demo. And what's the magic?
It starts automatically, but if it doesn't start in 2 seconds, we'll give it a nudge. Oh, it started, but we're not getting any audio. It's running. It was moving here. Do you know how we get audio on their demo?
By the way, demos never work. And that's why we pre-canned it. And even then, it never works.
I'm sorry? Is it?
Anyway, what this demo shows is apiary
We've
running.
built a demo social network on our open source prototype of DBOS. You can log in, send posts to others, and read posts sent by others. All these names and posts are of course fabricated. In this demo, we'll show how DBOS can help you detect, respond to, and recover from a cyber attack, like someone using a compromised admin account to steal users' personal information. Let's say a bad guy has stolen the password for one of our admin accounts. They want to exfiltrate the private posts of certain people. First, they'll read all of Mike Stonebreaker's posts. Then, they'll send them to the account of their associate, John Q. Hacker. And now, logging in to John Q. Hacker's account, I can see all the stolen messages. Now, this admin account is allowed to access sensitive data, and it's allowed to send messages. And neither operation on its own is too suspicious. But the composite event of reading sensitive data, then sending it to someone else, is very suspicious. And because DBOS monitors the provenance of everything, including application tables and messages, it can detect this composite event, flag it, and proactively suspend the compromised account, all within a couple seconds. So if the bad guy tries again, they can't exfiltrate anyone else's messages because DBOS has proactively suspended the admin account. Then, after you've found the suspicious event, DBOS gives you some options for how to respond. To show you these, I'll switch over to another DBOS admin terminal. For example, if you want to see exactly what was exfiltrated before the account was suspended, you can do that with a single SQL command. You run it, and now you can see exactly which users had their accounts breached. You can also take further measures, including basic measures, like suspending John Q. Hacker, and more complex responses, like rolling back all changes made by the compromised admin account, or investigating all users who have interacted with John Q. Hacker. So what we've shown here is that DBOS provenance and centralized logging lets you automatically detect and respond to suspicious composite events that happen in multiple parts of your system, then recover from them.
Okay, so we have two environments which you're welcome to try. So we have the demo you've seen is an apiary application that we wrote running on top of our stuff, running on top of Postgres. So it's all open source. Our stuff is open source, Postgres open source. Life is good. So try it out. Of course, the only problem is Postgres is not very fast relative to VoltDB. So anyway, try it out. It's on Git. All of this is on GitHub. Go have at it. And say, basically, where you can get it is on the slide. So that's an open source world, which you're welcome to do anything you want to with it. And, whoops, back up one. So the performance numbers that I gave you were all on top of VoltDB. And that's simply fast. And so we're using a closed source, very fast version, and an open source, not very fast version. So one of them is available. All our stuff is open source. This is an MIT, Stanford, Carnegie Mellon project. And we want to move the closed source version into something that's fast and open source, and we're working on that. That takes money, which we've gotten from your favorite guys, the venture capitalists. And we're very interested in talking to all of you as to what you think we should do next, what pieces of this interest you, where we should go with all of this. And I think that's the last slide, isn't it?
Well, what you just said,
Okay.
We'd love to have you try it, and please contact us. And I'm MCODEN, mcoden@mit.edu. And if you could talk to us, tell us what we should add to GBoss and what features you'd like to see, what programming languages, what API libraries, et cetera. We'd love to hear that, and if you want to contribute code, that would be great. And we'd love to have some people try it out. And now we can, any questions? We've got, 3 minutes for questions, I think.
First of all, congratulations. It's rare that the fundamentals of computing are rethought in this way. So congratulations, young people over there who...
Thank you. Can you give your name and affiliation?
Yes, my name is Bar Lockwood. I've been in the profession for about 20 years now in cybersecurity. The question that I have for you, which really intrigued me, was the notion of a total transaction being brought together rather than going out and grabbing data and bringing it in. Are you suggesting that the ledger itself would exist in the database such that
Yes.
you wouldn't?
All
Yay.
all data. Tattoo this on your brain. All data, every single bit of it, goes into the database system and gives you all these nice properties.
That's a game changer, absolutely, because then you're not managing multiple data sources. It's all in one thing.
Yes.
What kind of talent would you need to maintain a system like this? Obviously, SQL programmers like crazy, right?
So I think the simple answer to that question is you can get rid of your Linux system administrator.
Mm-hmm.
You can get rid of your Kubernetes system administrator. So all those people can go away, and they get replaced by a small, in my opinion, a smaller number of DBAs, because your world is all SQL, 100% of it, and everything is in SQL tables. So, and if you actually do this, your world is much simpler, as I've been trying to explain.
Thank you.
Yeah, I think it's really interesting to challenge the assumptions and look at how you try to rethink it. My question is this: in modern architectures, unless you're building a really simple service, you go for microservice architecture with multiple storages and multiple services. Have you thought how, like, do you need something additional, like a distributed transaction coordinator or anything, to benefit from this type of things you are discussing in a really a little bit bigger, complex, multi-microservice system?
Okay, so you asked a couple of questions. The first one is, if you insist on putting your application data in, say, Oracle, then you're running 2 DBMSs because Oracle is too slow for us. And so we're running our stuff in one DBMS, your stuff in a separate DBMS, and now distributed, you're basically in a distributed transaction world. And we hope not to have to write XA for everything. And so if you're willing to put all your stuff in one place, you get all the benefits without essentially any work. But if you insist on using multiple DBMSs, so be it. You just right now get less services.